Hello, my name is Ryan, and today we're going to be looking at Lab 4 Oscillations. In this lab, we're going to be analyzing the motion of a ball hanging from a fixed point by a spring after it is released. And since both the x and y components of the initial net force acting on this ball will be non-zero, we're going to see position oscillations in both the x and y directions. Now, the periods of these two oscillations don't actually have to be equal. And in this example, they're not going to be. We're going to see that later on. The physics principles we're going to be using in this lab are the momentum principles. We're also going to be looking at the energy principle, mainly this idea that if no work is acting on the system, then the total energy has to be the same. So all the components of the energy, or the different kinds of energy, potential and kinetic, they're all going to add up to be the same at any given point. Also, we're going to be looking at, or we're going to be using Hooke's law, which is for spring force calculations. Now here is our tracker video for the observed motion of the spring. As you can see, our axis is in line with the fixed point, and this spring here is what is attached to the mass. And so, as we can see, the range of motion follows an oscillatory pattern in both the x and y directions. And this data we were able to put into a spreadsheet, an Excel spreadsheet that we will import and use with our code later on, as we will see. We now use the formula for the period of oscillation, moving the spring constant over to the left side in order to solve for it in this instance, and then use Hooke's law as discussed earlier in order to find the relaxed length of the spring. We'll need these two components for our code. In GlowScript, we record the mass of the ball as well as its initial position and velocity, the force of gravity, the spring constant and relaxed length of the spring that we found earlier, and also using Hooke's law, we find the length of the spring at the current moment, the L hat vector, as well as the force of the spring. We use the energy principle and formulas in order to calculate the kinetic energy as well as the potential gravity and spring energies, and then adding them together to achieve the total energy of the system. And then finally, we have a loop to calculate the predicted forces as well as the updated position and velocity of the system. And as we see, the model predicts the motion of the ball pretty accurately as we've observed it in the video. We can allow these graphs to run while we take a look at the what does it mean questions. Now, the two questions that we have are, is the energy principle satisfied by the model, and how well does our model actually fit our x and y position oscillations? Now, if we look at our change in energy over time graph, we can see that although each of the different kinds of energy, the kinetic and two potential energies, these are constantly changing, the total energy of the system never changes. And this is exactly what we'd expect to see, and it does fulfill the energy principle that if no outside work is being done on the system, there's going to be no change in the total energy of that system. If we look at our x position over time and y position over time graphs, we see that for the most part the model well predicts the two different kinds of oscillations, but we do notice that the prediction gets a little bit off, and it seems like it's shifting over more to the right than the experiment, suggesting that the model overpredicts the period of the x oscillation. And if we look at the y oscillations, we see that it seems to be underpredicting or overpredicting the amplitude of these oscillations. Now, if we take these two pieces of information together, the most likely conclusion we come to is that we're over-predicting the mass in our model, because if we, again, go back to our period equation, we notice that an over-prediction of the mass will cause a greater period that we'll see. And then, of course, if we overpredict the mass, then we'll get a greater force of gravity, which would account for the greater amplitude of the y position oscillations.